In this video, I'd like to give an example of expressing partial fractions when we have a repeated linear factor. So notice here, there is a repeated factor of x plus 2. So we need to be careful about how we deal with situations where one of the factors on the denominator is repeated. And firstly, when we're expressing partial fractions, we decide what form we want this to be expressed in. So starting with our 9x plus 9 over x minus 1. The first thing we could do is express this in partial fractions of the form a over x minus 1 plus b over x plus 2 all squared. But we need to be careful here because this is not quite right. Because notice that this expression here is quadratic. So this expression on the numerator needs to be one order less than the expression on the denominator. So we need this to be linear. So then rather than just a constant b here, what we need is a linear term, bx plus c. But we can actually do a bit more with this. So let's take bx plus c over x plus 2 all squared. And let's notice that we can express this in the form d over x plus 2 plus e over x plus 2 all squared. And notice that that is true, because if we take a common denominator of x plus 2 all squared, this becomes d lots of x plus 2 plus e all over x plus 2 all squared. And then all we need to do is to find the values of d and e that make bx plus c identical to d lots of x plus 2 plus e. So we can further break down our partial fractions in this case to a over x minus 1 plus some constant b, and notice I used d before, but this is just some unknown we need to find, so this is not the same b as this one, b x plus 2 plus c x plus 2 all squared. And this is the general form of partial fractions we want when we have this repeated linear factor. We have one fraction which has the singular linear term, and then we have the square of that single linear term here. Okay, so let's now try and deal with this question. Well, what we want to do is we want to write all of this expression with a common denominator. In particular, we want a common denominator of x minus 1, x plus 2 squared. So this first fraction we need to multiply on the numerator and the denominator by x plus 2 all squared. So we get a lots of x plus 2 all squared over x minus 1, x plus 2 all squared. This next fraction, we need to multiply the numerator and the denominator by x plus 2 and x minus 1. So doing that, this becomes b lots of x plus 2, x minus 1 over x minus 1, x plus 2 squared. And finally, this final fraction, we need to multiply numerator and denominator by x minus 1. So this becomes c lots of x minus 1 over x minus 1, x plus 2 squared. And now we have a common denominator, so this is equal to a lots of x plus 2 all squared plus b lots of x plus 2, x minus 1 plus c lots of x minus 1 all over x minus 1, x plus 2 squared. But this is identical to 9x plus 9 over x minus 1, x plus 2 squared. So we need to find the values of a, b and c which make this true. Well, this is an identity. It is always true. So we know that these numerators are identical. And if this is always true, we know it is true for all x. So in particular, we can substitute in any value of x here. But if we look carefully, what might be a sensible value of x to try? Well, notice if x is negative 2, this bracket and this bracket are going to be 0. So if we let x equal negative 2, this left-hand side is minus 18 plus 9, which is minus 9. This is a times 0 squared, so that is 0. This is b times 0 times minus 3, which is 0. And this is c times minus 2 minus 1, so minus 3c. So what do we have there? We have minus 9 equals minus 3c. So this gives us c equals 3. Well, what might be another sensible value to substitute? Well, if we let x equals 1, these two brackets here are going to be equal to 0. So if x equals 1, we get 9 plus 9, so 18, is equal to a times 1 plus 2 is 3, 3 squared, so 3 is 9, so 9a, and then the remaining two terms are both 0. So what does this give us? Well, this gives us 18 equals 9a, so a equals 2. Okay, well, we've still not found b, and we've got two different approaches here. There's not really another x value we can substitute in to make a bracket 0. So, but we did say we wanted this to be true for any a at all. So, for any x at all. So we can now just pick any x value at all and substitute it in. So this is one way of approaching this. So I'm going to pick x equals minus 1. But you could pick anything. If you really wanted to, you could let x be 100. But if we let x equals minus 1, we get minus 9 and 9, so we get 0 equals a lots of minus 1 plus 2 is 1, so 1 squared, so a, plus b lots of minus 1 plus 2 is 1, minus 1, so plus minus 2b, and then here we get minus 2c. But we know the values of a and c, so this gives us 0 equals 2 minus 2b minus 6. So this gives us 4 equals minus 2b. So b equals minus 2. So we've now found our values of a, b and c. Well, there is an alternative way of doing this last step. And the alternative is to look at equating coefficients. So we could equate the constant terms, we could equate the x terms, or we could equate the x squared terms. It really doesn't matter which ones you do. But I'm going to equate the coefficients of x squared. So on this left-hand side here, the coefficient of x squared is 0. There are 0 x squared terms. On the right-hand side, well, we're going to get an x squared here when we square it out, and that's going to be multiplied by a, so there's going to be a lots of x squared. And here, we're getting an x squared here, multiplied by b, so we get b lots of x squared. And then we're not going to get any x squared in this final term. So what do we get? Well, we get b is equal to negative a, and we knew a was 2, so no, b is negative 2. So that's an alternative method to find that value of b. So what can we conclude? Well, we knew that we wanted to find a, b and c in this form. So we can say that 9x plus 9 over x minus 1 x plus 2 all squared is identical to 2 over x minus 1, which was our value of a, minus 2 over x plus 2, because our value of b was minus 2, plus 3 over x plus 2 all squared. And that is 9x plus 9 over x minus 1, x plus 2 squared, expressed in partial fractions.